In topic 5, we need to kind of explore the idea of coming up with a polar form of a complex number. So let's kind of just review a few things, okay? So we're going to let z equal x plus yi be a complex number specifically in rectangular form, okay? So we have seen z equals a plus bi. We already know that A really represents some distance along the real axis, which for us is kind of like the x-axis, and B represents some distance along the imaginary axis, which for us is like the y-axis. So we can say, hey, we can rewrite this as z equals some distance along the x-axis plus some distance along the y-axis, but we make it imaginary by tacking on that I. And what we really want to make clear to the reader is that this is rectangular form. Okay. We know already that when we're dealing with rectangular form, we're dealing with x's and y's. When we're dealing with polar form, we're dealing with r's and thetas. So we're just writing our complex number in something that we can kind of recognize as rectangular form. Okay. So we have seen that z corresponds to some point xy in the real plane. Okay, so we're real comfortable just writing our complex numbers like this for now. Okay, because it really just represents a point in the xy plane just like it represents a point in the complex plane. Okay, now recall we have to kind of go back and discuss a few things from like 10.1, 10.2, specifically 10.1. Okay, so we have the point xy can be converted to the polar coordinate r cosine theta comma r sine theta, where r equals the square root of x squared plus 1, and that did get kind of broken up. This is like r equals over here. And then tangent of theta equals y over x. So when we were in 10.1, we found that there were these relationships that really come from just a right triangle that were really, really important for us, okay? And they allowed us to go from this world of x's and y's to this other polar world where we have r's and thetas and vice versa, okay? So we had to know that r equals the square root of x squared plus y squared, just to play on the Pythagorean theorem. We have to know that tangent of theta relates y over x. We also had that x was equal to r cosine theta and y was equal to r sine of theta. Now, if this is a little fuzzy to you, pause this video and go back to your 10.1 notes and kind of remind yourself of this stuff because it's going to be really important in just a bit. Okay? Now, that finally leads us to this idea of polar form of a complex number. Okay? So, therefore, the complex number z equals x plus yi can be written in the form, okay? We're basically taking the x and the y and we're using these little guys, these substitutions we'll say for x and y. So we're going to take the x and y and z equals x plus yi, and we're going to rewrite the x as r times cosine theta and the y as r times sine of theta. So all we've done was take this and plug it in here and this and plug it in here. And that comes from this right here. Okay. So we have that z equals r cosine theta plus r sine theta times I. Okay. Now, a lot of times what we're going to do is we're going to acknowledge, hey, we have these two terms here and they have something in common. They have an r in common. So we can factor the r out, and then we get this format right here. So it is very common to see the polar form of your complex number written as r times, and then in parentheses, cosine theta plus sine theta times I. Okay, now the I. Ordinarily, you have the I at the end of your imaginary part, okay? But with this, when we have sine of theta, we want to make sure that it's really, really clear that the I is not part of that argument. We don't want it to get kind of mixed up with the argument. So it is super common to see the I in front of the sign. Okay, so when you write your complex numbers in rectangular form, you put the I at the end. This right here is kind of like our standard form up here in the corner. Okay, but when you're doing the polar form of a complex number, it's very common to put the I in front of sign. Okay, again, it's just we don't want it to get mixed up with the argument. All right, so we're going to go back. We're going to explore the real plane and the complex plane again, and we're going to make sure we understand there's this relationship between complex, real, and then eventually polar. Okay, so explore the real coordinate plane and the complex plane by completing the following. Okay, we are going to label again. Let me actually shrink this so we can hopefully see all of it. That's close enough. Okay, so for the real coordinate plane, we've got to make sure we understand the two axes. This is the y-axis. This is the x-axis. Okay? Now we're going to do things a little differently this time. We're trying to really understand that this all relates to the complex plane. Okay? So this time, let's draw an angle. Let's call it theta in quadrant one, so Q1. Okay? So we could draw some angle. Okay? We've drawn an angle in quadrant one. Plot and label a point XY on the terminal side of theta. Okay, done. We've got some point X comma Y. And then it says use this point to create a right triangle. Well, that's cool. We can do that. All right. And then it says label theta, R, X, and Y. Well, this is our X. This is our y. We know theta is this angle right here. And then remember, r is the distance from the origin. So when you're dealing with like the polar world, you draw your angle from your polar axis, which is kind of like our x-axis. So you draw out some angle, and then if r is positive, it's some distance from the pole or the origin to whatever your point is. So we would say this right here is r. Okay? Now we're going to do the same thing for the complex side, then we'll answer the two questions kind of underneath these graphs. So the complex side says label the x and y axis. Now remember, when you're in the complex plane, we want to call the x-axis the real axis. So it works for us like the x-axis does in the real plane. And the y-axis is what we call the imaginary axis. And again, in the real plane, this would be kind of equivalent to the y-axis. Okay. We want to draw some angle in quadrant one. All right. So we have some angle in quadrant one. And this time it says plot and label the number z equals x plus yi on the terminal side. Okay. Use this to create some kind of a right triangle. Okay. And then it says label x, y, r, and theta. Easy. This is x. This is y. This is theta. And remember, r is kind of like our radius here. It's basically the distance. If you're in the polar world, it's the distance from the pole or the origin to whatever point you're interested in. So this would be r. So even in the real plane and the complex plane, we have a situation that's very polar in nature where we have an angle and we have a value for r. Okay? So really quickly, the two questions that we have to ask ourselves for each side. What is the rectangular form of all points in the real coordinate plane? Well, that would just be xy. Okay? And then what is the polar form of all points if we're kind of like morphing into this xy plane? We would just use r comma theta. We can still draw an angle theta in the xy plane. We can still go a distance from the origin to some point, which is r units away from the origin. Okay, now for the complex plane, it says, what is the rectangular form of complex numbers? Now remember, the rectangular form of a complex number is z equals x plus yi. And then what is the polar form? Well, for polar form, we have to be, I think my computer's about to die. Hold on. It does not last as long as it used to, you all. Battery's dying. Okay, so it says, what is the polar form of a complex number? Well, remember, when you're dealing with polar form, you need those r's and you need those thetas, okay? So we had that z equals r, and then you want to find a way to replace x. Well, we can write x as cosine theta, and then we need sine of theta to be our y. And then just don't forget, a lot of times we put that I in front of the sign. We don't want it getting mixed up with the argument, okay? So we have all these connections between the rectangular plane and the complex plane. We've drawn basically the identical picture from one plane to the next. We just have a point xy versus a number z equals x plus y squared. We have the same theta, the same x, the same y, the same r, okay? So there is certainly this connection between rectangular and complex and now polar. Okay, so we can use the rectangular plane or the real plane and the complex plane to still plot these polar coordinates. Okay, so just make sure you really understand the connections between all of these pieces. Okay, now one last thing, and we've kind of already talked about this, but let's really drive this point home. I have it kind of here tucked between these two examples. I have recall, let z equal a plus bi be some complex number. And remember, we could call that z equals x plus yi Same difference, okay? The magnitude of z, denoted by like magnitude bars, z, they look kind of like absolute value bars, is the distance from the origin to the point A, B, okay? So underneath this, we have example 8, short answer. Anytime I have the direction short answer, I don't know what to call it. So I'm just like, ah, short answer. All right, so for example 8, we're going to use this little recall definition thing up here, okay? Knowing everything we have learned so far, real plane, complex plane, polar coordinate system, rectangular coordinate system, if you don't want to call it the real plane, these three worlds, okay? Knowing everything we've learned so far, what else does the magnitude of z equal, and how did you arrive at this conclusion? Well, let's mosey up here a little bit. Okay, so when we're talking about the magnitude of z, we want to represent the magnitude of z as some number that is the distance from the origin to the point or to the number z. Okay, so we call this right here, let me do it in another color just so it's super clear. And we've played around with this already, but now we're driving the point home. We know that the point z is some distance away from the origin, and we call that the magnitude of a complex number. Well, when you're in the polar world, it's also just r. Okay, so r, which is your distance from the origin or your distance from the pole along some angle, that's how you get these polar coordinates. It's really the same thing as our r. So we would say the magnitude of z equals r in the polar world. And how did we arrive at this answer? Well, we kind of looked at the graphs first of all, okay? But we also, in a previous example, we looked at the Pythagorean theorem. We looked at the formula for R. We looked at the formula for the magnitude of Z. Remember, R equals the square root of x squared plus y squared, and the magnitude of Z equals the square root of a squared plus b squared. But remember, that's if you have Z equals a plus bi. If we have z equals x plus yi, then we would get x squared plus y squared. So these two things are the same, which tells you that r and z are, well, really the same. Okay, so we've got different ways that we can come to this conclusion. We can look at it graphically. We could just look at the formulas. We could also just flat out find r, and we could flat out find the magnitude, and they're going to be exactly the same thing. Okay, so we've got a little bit more, I think, for this video. This one has several examples, if I remember correctly. Yeah. I got to make sure my pages don't get mixed up here. Okay, so example 9 says, consider the complex number in rectangular form, and we have z equals 3 minus 3 root 3i. Okay, so part A says, plot the point and determine the quadrant that the point lives in. Well, remember, we could treat this like x, we can treat this like y, so this is basically equivalent to the ordered pair, 3 comma negative 3 square root 3. Well, for those of us that aren't, maybe number smiths, all right, maybe we don't know what negative 3 root 3 is, but that's okay. We can use our calculator to estimate and get some kind of decimal equivalent, okay? So we have negative 3 times the square root of 3. Well, it is negative, where do I have? Yeah, I just want to make sure I'm good. So it's negative 5.196. So let's say it's about negative 5.2. Okay, it's not exact, but it's pretty close. So we're going to say this is about negative 5.2. Okay, so part A says plot the point and determine the quadrant the point lives in. Well, we would want to start at the origin. We want to go a distance along the real axis or the x-axis, 3 units. And then from there, we want to drop down along the y-axis or the imaginary axis, negative 5.2. So down 1, 2, 3, 4, 5, and a little bit more. So this right here is z equals 3 minus 3 square root 3i. Okay, now part B, we're getting ready to write this in polar form. Okay, so it says find r and theta and then write z in polar form. I probably didn't give you quite enough room here, so try to write kind of small, be very neat and organized because this is going to be a teensy weensy bit scrunched. Okay, now r, remember r is equal to the square root of x squared plus y squared. So we've got an x value, we've got a y value. So we're going to say r equals the square root of 3 squared plus negative 3 square root 3 squared. Now remember, -3 times the square root of 3, that is quite literally a product. And when you have a product raised to a power, you raise each factor in your product to whatever that power is. So be careful when you simplify here. 3 squared we know is 9, okay? And then -3 right here squared is 9. And then square root 3 squared, the square root and the exponent of 2, they just unravel each other, so we get 3. So this is really the square root of 9 plus 27, or the square root of 36. So we can say with a fair level of confidence that R is 6, okay? Now, that's kind of the easy part. Theta we have to be a little bit more careful with. So theta, we have to go and remember that, well, tangent of theta is equal to y over x. So that is something that you should remember from like 10.1, 10.2. So tan theta, we know it has a relationship of y divided by x. And that's super convenient for us because guess what we have? We have a y and we have an x, okay? But we want to find the value for theta. So in order to do that, we take inverse tangent of both sides of this right here. And that essentially tells us that theta equals inverse tangent of y over x, okay? Well, that means theta equals tangent of, well, we've got -3 root 3 over 3. So that tells me that we're looking at tangent of negative, whoops, don't write it like that, y'all. We have tangent of negative root 3. Now, negative root 3, that is definitely like unit circle, okay? So when you have like 1 over root 3, or if you have root 3, that's something on your unit circle, and it's some ratio at either pi over 6, pi over 3, negative pi over 6, or negative pi over 3. Because remember, when we're talking about inverse tangent, it is defined from negative pi over 2 to pi over 2. So let's think about this. So this is negative pi over 2. This is positive pi over 2. Okay. And we have tangent as some negative ratio, negative root 3. So that's definitely going to be something in quadrant 4. Okay. So we've got 2 points that we need to look at. We've got this one and we've got this one. This one is root 3 over 2 comma negative a half. And this one is 1/2 comma negative root 3 over 2. So which one has the ratio where when we take y and we divide it by x, we get negative root 3? Well, for us, that's going to occur. Let's see. Let's try this one. So let's try pi over 3. So this one right here is pi over 3. So when I look here, remember, tangent is y over x, or sine over cosine. So we get negative root 3 over 2 divided by a half. That's negative root 3 over 2 times 2 over 1. Well, this is good. The 2's are going to cancel, so we get negative root 3. So we're dealing with negative pi over 3. Okay? So we get tangent equals negative pi over 3. Okay? But let's really think about this. Let's mosey back just a smidgen. Well, maybe more than a smidgen. Let's mosey back here. We have polar form of a complex number. We go through some review stuff, and then we talk about the actual polar form of the number. And what we haven't talked about yet was this right here. Okay, now we have polar form of a complex number, z equals r, and then in parentheses cosine theta plus I times sine theta. But we have conditions. R has to be greater than or equal to 0, and theta must be from 0 to pi over 2. Well, unfortunately, when we go back to our problem, our theta isn't between 0 and pi over 2, or, well, 0 and 2 pi. I think I said pi over 2, 0 and 2 pi, okay? We definitely have something that's outside of that. So we need to find a coterminal angle from 0 to 2 pi. Okay, so all I really have to do is take theta, and then I can just add 2 pi, and that'll put me somewhere between 0 and 2 pi. So that's going to be negative pi over 3 plus 2 pi. I told you we weren't going to have quite enough room, and I really am sorry about that. Okay, so that's going to be negative pi over 3. Now, 2 pi with a denominator of 3 is going to be 6 pi. Okay, so we're going to get plus. Do I like the 6 pi? I have a different number there. I don't know if I like that. Yeah, we're good. So we're going to get 6 pi over 3, which is 5 pi over 3. And if you're in the unit circle, positive 5 pi over 3 is right here. So we're good. We have a value that's between 0 and 2 pi. Okay, so we're not done yet. We're getting there though. Okay, so there's our theta. Whoops, I don't know why I put the double line through that. I think I was doing an equals. So there's our theta. Don't forget we had our r up here. So if we want polar form, we're going to get z equals, remember it's z equals r times cosine theta plus I times sine theta. So we want 6 times cosine of 5 pi over 6 plus I times sine of 5 pi over 6. And this is it. So I'm going to highlight this one so we don't lose it. Okay, so that, whoops, I went a little overboard. Let me do it again. So this right here is polar form, okay, of z equals 3 minus 3 square root 3i. Okay, so you've got to find your r value. That's pretty easy. You've got to find your theta, which not terribly difficult. Nothing was really hard. It's just you got to be really careful. So you got to use your inverse tangent. You have to remember that inverse tangent is defined from negative pi over 2 to positive pi over 2. And then depending on what it spits out, if it's in quadrant 4, it could easily give, well, it's not easily, it's going to give you a tangent ratio that is negative, which is going to give you a negative angle from the x-axis down to negative pi over 2. So then all you have to do is take that angle and add 2 pi, and that'll give you something that is appropriately between 0 and 2 pi. Okay? One more example, and then we are at the end of this video. So example 10 says, consider the complex number in polar form, z equals negative 3 cosine 60 degrees plus I sine 60 degrees. Okay, what are the values of r and theta? Well, here we have, whoops, we have that r is equal to negative 3 and theta is equal to 60 degrees. Okay, so it says we're going to do two things. We're going to plot, oh, I've got a typo right here. We're going to plot the point in the complex plane, and then we're going to find the rectangular form, okay? So as long as we have r and theta, we can get x and y, okay? So as long as we have the x and the y, we can then get the rectangular form of the complex number, okay? So let's first start with just plotting this number. Okay, so we've got basically polar coordinates. Okay, so you have to remember that when you're dealing with polar coordinates, you have a pole, you have a polar axis. Okay, you sweep open some angle. So in this case, our angle is positive 60. So positive 60, I'd be like, no, no, about here. So that's our theta equals 60 degrees. And then what you want to do is you want to find r. So if r is positive, it's going to be some distance from the pole along the terminal side of your axis, okay? If r is negative, it's going to be some distance from the pole in the opposite direction of your terminal angle, or I think I said your terminal axis. Let me start over, okay? So basically, if r is positive, it is some distance from the pole along the terminal side of your angle, okay? If r is negative, it's going to be some distance from the pole in the opposite direction of the terminal side of your angle, okay? Well, our r is negative, so we're going to go 1, 2, 3 units, and that's going to put us squarely in quadrant 3. Okay, so now let's see if we can get the rectangular form. Now remember, as long as you have an r and a theta, you can get an x and a y. Okay, what we have to remember is that r is equal to the square root of x squared plus y squared. Okay, we have to remember tangent of theta equals y over x. We have to remember that x equals r cosine theta, and we have to remember that y equals r sine theta. Those are kind of those relationships, those main relationships that we have to remember from 10.1 and 10.2. So which of those would we need? Well, we're going to need a value for x, and we're going to need a value for y, because when we're in polar form, we have r's and thetas, but we need x's and y's. So let's figure out what x and y are. So remember, x equals r times cosine of theta. So that's going to be negative 3 times cosine of 60 degrees. Well, if you're in the unit circle, 60 degrees has a point on the unit circle of 1/2, comma, root 3 over 2. Sorry, it's a little scrunched. Okay, so this is really -3 times a half because cosine of that point, that's going to be the x coordinate. So we get -3/2. So that is the x coordinate that we're going to need for our complex number. We need y. Y is r times sine of theta. So that's going to be -3 times sine of 60 degrees. Okay. 60 degrees, that's pi over, I think I said pi over 6 at some point. This is pi over 3. So 60 degrees is pi over 3. And we have that sine of 60 degrees is root 3 over 2. So we get -3 times root 3 over 2. So we have -3 root 3 over 2. That is our y. Okay. Well, what we're looking for is rectangular form of a complex number. And remember, rectangular form is z equals x plus y I. Okay, so we're going to get z equals -3/2 plus, nope, minus, since our y is negative, we're going to put a minus in here. And let me scoot it over just a little bit, and I'll even do a different color so it's easier to see. So we're going to get z equals -3/2 minus 3 root 3 over 2 times I. And this is our final answer. Okay, so we've kind of covered not a lot, but then a lot all at the same time. So just as a kind of a quick recap, we need to make sure you understand what polar form of a complex number is. Make sure you really understand the relationships between the real plane, the complex plane, and then these polar coordinates. Make sure you understand that the magnitude of z is the same thing as r. Did I? And then finally, make sure that you can convert a complex number that's in rectangular form to polar form, and make sure you can take a complex number that is in polar form and convert it back to rectangular form. Okay, so again, we've covered a lot, but not a lot. There you have it. All right. And I think, yeah, that's it for this one.